Hi, Chemistry 3101. This is Chapter 10, where we look at radical reactions, right? If you think about all these reactions that we've looked at so far in Organic Chemistry 1, we spent all of our time, well, most of our time anyway, looking at double-headed arrows, which represent the flow of 2 electrons. And in this chapter, we're going to talk mostly about fishhook arrows, which represent the flow of 1 electron, right? Because we know that when we have an unpaired electron, we call that a radical. Well, let's talk about radicals some more. It says a bond can be broken in a couple of different ways. You can have what's called heterolytic bond cleavage, which forms ions, and you can have homolytic bond cleavage, which forms radicals. So if we have a bond between 2 elements and both of the electrons end up going with one of those elements to make an anion and a cation, that is a heterolytic bond cleavage. We saw that occur many times in ionic mechanisms. But we also talked about homolytic bond cleavage. If you remember in Chapter 6, when we talked about bond dissociation energies, right? We talked about bond dissociation energies, and I told you that those bond dissociation energies that we looked at were measured from homolytic bond cleavages. So homolytic bond cleavage is where you have a bond between 2 elements, except one of the elements gets one of the electrons from that bond, and the other element gets the other electron from that bond. So you end up with a pair of radicals, right? Because radicals have unpaired electrons. And of course, as I told you on the first slide, you notice that the first arrow is a double-headed arrow that represents the flow of 2 electrons, whereas each one of these curved arrows represents the flow of 1 electron, right? And we call these the fish hook arrow, okay? The fish hook arrow. So again, the double barbed arrow shows the movement of 2 electrons, and the single barbed arrow is what we call the fish hook, and that is showing the motion of 1 electron. So we talked about this a little bit, in this class, but not a ton. Well, I want to talk to you a little bit about the structure of a radical. Okay, what is the structure of a radical? But before we do that, I want to talk about the structure of a carbocation and a carbanion. So this will be review to you, right? We've talked about carbocations, as is shown here, many, many times in this class, and we've seen many, many carbanions in this class. Well, if I look at a carbocation, we know that a carbocation carbon is sp2 hybridized and that its molecular geometry is trigonal planar, right? That's why he has this flat square here, is to show you that it's flat, it's planar, right? Flat as a pancake. Whereas a carbanion, we know that carbanions are trigonal pyramidal with respect to their molecular geometry. Why? Because they have the lone pair, which takes up an sp3 orbital, and so that pushes, these bonds down like this, but we end up with a trigonal pyramidal molecular geometry. So you might think, well, if I have a radical, it's kind of like in between a carbocation and a carbanion. It doesn't have 2 unpaired electrons. It doesn't have 2 electrons in an sp3 orbital. It's only got 1. Okay, so what's that going to look like? Well, let's take a look. It says radicals actually appear to be trigonal planar, like they're sp2 hybridized, or we could view them as being a shallow trigonal planar, or having a shallow trigonal planar molecular geometry, in that it's quickly interconverting. So the barrier of inversion here, we'd say that's a really low barrier to inversion. So essentially, the take-home message is this, okay? You can strap your skates on to this one. You can set your watch to this one, okay? In Chemistry 3101, hear me out very loud and clear, you can view a radical as being trigonal planar, okay? So whenever we see a radical and we're considering its molecular geometry, we can think of it as being trigonal planar, because even if we think of it as being a pyramid, it's so shallow, it inverts so rapidly that essentially, again, it kind of takes away that idea, and we just think of it as being trigonal planar, okay? So, well, let's talk about the stability of free radicals, right? We spent some time talking about the stability of carbocations. We said that a tertiary is more stable than a secondary, is more stable than a primary, which is more stable than a methyl. Well, I have some good news to you. If you understood the stability of carbocations, radicals follow the same stability trends as carbocations, okay? Why? Because they're both electron deficient, right? We know that the more R groups that you have surrounding that radical or that carbocation, it donates electron density towards the radical, okay? It kind of donates electron density that way, and what does that do? It stabilizes the radical. So what do we learn? In a nutshell, a tertiary radical is more stable than a secondary, is more stable than a primary, and that's more stable than a methyl. Okay, and that's going to be important for us because we're going to look at radical mechanisms wherein we're going to form tertiary radicals and secondary radicals, and we have to evaluate, well, which one's going to be more stable. Well, it follows the same trend as carbocations. And so what we see is if we look at the bond dissociation energies of the hydrogens that would be abstracted to produce any one of these radicals on this page, we see that bond strength is inversely proportional to carbon radical stability. What do I mean by that? It means that the more stable the radical that you would get, the weaker the bond. Just take a look at this here, right? If you were to break this bond between this carbon and this hydrogen homolytically, okay, I'll just demonstrate with one. Those are my two fish hooks. What would you end up with? You would end up with this. You'd end up with a tertiary radical, right? And a tertiary radical is more stable than what you get. I guess I'll do one more. Let's do it with methyl. A tertiary radical is going to be much more stable than a methyl radical, isn't it, right? From this, you would end up producing this radical, right, where you have no R groups, okay? So the same rationale for all of these. And so the stability of the radical is manifested in the bond dissociation energy, right? You see that the more stable radical you get, the weaker the bond is, okay? Why is it weaker? Because it's easier to break, because you end up with something that's more stable, right? Why does this cost so much more energy to break, this carbon-hydrogen bond? It's because what you end up with is not stable at all, right? Getting a methyl radical is very unstable. All right, so make sure you understand the relationship between bond dissociation energy and the resulting radical. What's produced after you break that bond homolytically? Well, just like carbocations, radicals are stabilized by resonance, right? And this is something that we've seen, I think, briefly over the course of Organic Chemistry 1. But you know how we talked about carbocations and all the different resonance structures that we could draw? That was way back in chapter 2, earlier on in the class. A lot of the resonance forms that we're going to draw of radicals will be based off of an allylic radical. Okay, not all of them, but a lot of them will be based off of this. So where you have a vinylic position, so you should know that on a double bond, these two positions that I have highlighted in yellow, those are vinylic, and the one that's highlighted in green, that's an allylic position. And so you can see that this has another resonance form where we can draw that unpaired electron being delocalized, okay, using a collection of 3 fishhook arrows. And you should be able to do that, of course. So let's take a look at an example here. It says the more delocalized a radical is, just like a carbocation, the more delocalized a carbocation was, or the more resonance contributors we could draw, if you want to put it that way, the more stable it is. Now, a benzylic radical, as is shown right here, this is a benzylic radical, right? Remember, I've told you this several times, that if you have an aromatic ring, okay, if you have a carbon, right, it doesn't matter how many, this is called the benzylic position. It's the position right next to the aromatic ring. So that's a benzylic position. So if you have a radical there, as is shown in this first structure here on the slide, right, that's a benzylic radical. Well, it says benzylic radicals are more stable than allylic ones because the radical is delocalized over more carbon atoms, right? If we draw an allylic radical, we could just get some practice here. It's not asking us to do this, but we could draw it like this, and then we could practice drawing the fishhook arrows, right? I'm going to make a new pi bond here, so I need this electron and one of the electrons from the pi bond, and then the other one is going to go on the end like this. So what's my other resonance contributor going to look like? It's going to look just like this, okay? Now, if you're like, I think I need more practice on that, well, here we go. Let's try it. We've got the benzylic radical. You can see that the person drew in the first 3 fishhook arrows and the second 3 fishhook arrows. And let's see if we can draw the resultant radical after these 3 arrows. Okay, so we have this double bond remains untouched. This one remains untouched. But you can see that 2 fishhook arrows are meeting in between these 2 carbons. So we must be forming a double bond here. And again, one of those electrons came from this double bond, but the other one is ending up on this carbon here. So we have an unpaired electron here. And now you can see that we have another allylic radical here. So we can keep going and keep drawing resonance contributors. So let's practice. We've got a fish hook arrow that's going to form a double bond here. We're going to form a double bond with a second electron, and we're going to end up with an unpaired electron over here. So let's draw what that resonance contributor would look like. Draw our six-membered ring. This bond is untouched. This one is as well. Now we have a new double bond here, and we are going to have an unpaired electron there. Now, technically, that is the last resonance contributor. There are only 4. But we're going to round it out, and we're going to go back to the beginning. So I'm going to draw one more. Oh, where's my pen? There we go. Let's draw one more to complete it. And you can see that you have the allylic radical right here. So to draw the last resonance contributor, which again takes us right back to the beginning, we're going to make a new double bond here, restore our aromatic ring. That second curved arrow looks a little funky, doesn't it? Maybe there we go. And there we go like this. And I'm going to remove this square bracket because this is part of all the resonance contributors I'm drawing. And we go right back to the beginning. We have our aromatic ring like this. And there you go. And there you go. That's it. So again, these 4 are the resonance contributors. This is just taking me back to the beginning. But give me a thumbs up if you follow me on the concept of drawing curved arrows and fish hook arrows for a resonance contributor of an allylic radical. Just if you follow me on the concept, of course, I would expect that you would need to practice it. Everybody needs to practice this kind of thing. But the good news is that it's kind of like the same pattern repeated a lot. I'm not going to take anything away from it and say, oh, it's easy, because I don't think anything is easy in organic chemistry. But as long as you understand this pattern, hopefully you do notice that this pattern is repeated here, 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 and here. I basically repeated the same pattern a few times on the same slide, okay? So we see that happen a lot, where you have an allylic radical and you just keep drawing the same old 3 fish hook arrows. Well, besides a tertiary radical being stable, you can actually end up with radicals that are even more stable than a tertiary radical. And I bet you guys could probably guess where I'm going with that. And that would be something where we have resonance stabilization, right? If you look at an allylic carbon-hydrogen bond, check it out. It's even weaker than the carbon-hydrogen bond on a tertiary carbon. Why? Because you end up with an unpaired electron, not an unpaired radical. You end up with an unpaired electron, right? Which is resonance stabilized, right? And you could practice drawing your fish hooks here, you know. But anyhow, you end up with something that's resonance stabilized. And we just drew all the resonance contributors for a benzylic radical. So that's even more stable. Why? We've already answered that question today, because this, the benzylic radical, has 4 resonance contributors, whereas this only has the 2. Okay, so it's more resonance stabilized. Therefore, its bond dissociation energy is even weaker than that of an allylic carbon-hydrogen bond. Okay, I'm not going to ask you to memorize these numbers or anything like that. It's more understanding the trend. Right? What's the trend? The more resonance stabilized the radical is, the weaker the bond is. You know, that's about it. Now, in terms of unstable radicals, you know, bonds that have high dissociation bond energies, that would be something like a vinylic carbon-hydrogen bond. You can see the bond dissociation energy is really high, okay, 464 kilojoules per mole. Right, it's higher than a primary. It's higher than an allylic. Why is that? Because you end up with something that has no resonance stabilization. In fact, it's pretty damn unstable, okay? So you don't want to draw a lot of vinyl radicals, okay? A vinyl radical is like a no-no, okay? So I'm going to put a red X over that. Same thing with like a vinyl cation. Remember, I've told you this several times in the class. You're never going to see this in organic chemistry, okay? We don't see that. Okay, so we don't draw those. And again, that's the conclusion as to why the bond dissociation energy of a vinylic carbon-hydrogen bond, it's so high. It's hard to break that bond. Well, with all that in mind, you might be wondering, you know, what kind of question could you ask me about all this spinach that you've gone over this morning, Mr. Dion? And here are some questions, okay? 10.1 A and B, it just says nothing more than rank the following radicals in order of stability. So I'm going to call the first one A, call the next one B, call the next one C. Could anybody tell me out of A, B, and C, the ones on the top, which one would be the most stable? Yep, everybody's 100% correct. It's going to be B is the most stable. And as you all could tell, it's not a trick. It's just because it's a tertiary radical. So we'll put here most stable tertiary. Could anybody tell me which one of these would be the least stable? Yep, absolutely. Absolutely. Okay. So A is going to be the least stable, and that's because it's primary. Okay. Nothing. And if you're like, I hope the whole quiz is questions like that, I'm probably going to ask that. Yeah, absolutely. I think that's something that everybody needs to know. So there you go. All right. The next one is 10.1b. Let's see. If I call this one A, B, and C. Could anybody tell me which one is we'll start with the least stable. Which one would be the least stable of all these? Yeah, absolutely. Absolutely. Okay, you guys are faster than me. So let's see here. This is the least stable. Least stable because it's primary. Right? Oops. And of course, the secondary is going to be somewhere in the middle. But you can see that B is going to be the most stable. Most stable. Because it's the tertiary. Yes, all of my students are 100% correct. Great work, everybody. Excellent. Not a complex problem, but you know, something that you need to know. Everybody who studies organic chemistry needs to understand radical stability. The next one is just draw the resonance structures. Well, let's give it the old college try. This is something I strongly recommend. You sit down with a piece of paper. You start with this and you say, okay, I'm going to start drawing some resonance structures. So let's put a closed bracket to start. Here's my allylic radical. So I'm going to start pushing some arrows. So I'm going to make a new double bond here, break this bond, and put an unpaired electron up there. So let's draw what we get. I'm going to zoom in a little bit here just for my own sake. And we're going to end up with something that looks like this. Where now we've got a double bond here. This one is untouched. We have a methyl group here, and we have an unpaired electron up there. Well, looky. Now we've got another allylic radical. So let's run with it. Let's draw some more fishhook arrows. I'll draw them in blue just for fun. We're going to make a new double bond. We're going to take the other. Ooh, we end up with a tertiary radical this time. Let's draw that out. There we go. So it's going to look something like this. There we go. Perfect. There we go. Let's do the next one. So the next one is D. There's only one allylic radical, and that's this one here. Okay, so let's draw the fishhook arrow. So I'm going to make a new double bond here, and then I'm going to have an unpaired electron there. And so we'll draw the resonance contributor, which is going to look like this. There we go. So this one has no other resonance contributors, does it? Right? Why not? Because this unpaired electron, okay, this radical, is not allylic to this double bond. Okay, it's not allylic. So there's only that one resonance contributor. There's nothing else. Okay, the unpaired electron is not allylic to the other pi bond, and so there's only one resonance contributor, and we've drawn it. All right. So again, this is the kind of thing that I think would require practice. So you might want to go back to question 10.2. You can see we didn't do A and B. So you might want to go back and I would highly recommend tackling those ones, make sure you understand what's going on. Well, what I think is a really good problem, and I've seen this problem come up on an MCAT before, I've seen it come up on the ACS final before, is they phrase it a way that it's kind of asking two questions at once, right? It just says identify the weakest carbon-hydrogen bond in each of the following compounds. So you've got to connect a few dots, right? You got to say, well, weakest carbon-hydrogen bond. So that's related to what? Bond dissociation energy. So the lowest bond dissociation energy is whichever bond that's going to break that's going to produce the most stable radical. Okay? So now there's many types of protons on here. I'm going to just try a few here with you. In this first molecule, A, this is why the iPad is helpful, because you can draw in different colors here. So if I put a proton in red, this proton in blue, I don't know, put this proton in green, like that. Could anybody tell me which one of these would be the weakest carbon-hydrogen bond? Oh, this is good. We get some hot debate here. Okay. We got a few different ideas. All right, I like the way you guys think. Okay, so I see a few people are saying the blue one. Let's give it a shot. If you were to break this bond, right, homolytically, you'd end up with this. So let's draw what you'd end up with. You'd end up with this, or you have the double bond. Oops, double bond here. Okay, and then you'd have this radical like that. Okay, the problem is this is not allylic, because if this is my double bond, this is an allylic position and this is a allylic position. Where the radical is not an allylic position, so this is not resonance stabilized. Okay, I see that a couple other students chose the red proton, so I'm just going to move this out of the way. Let's see what happens if you were to break the bond where the red proton is. So you'd end up putting an electron here and then one here. So let's, oops, I didn't mean to do that. Here we go. So you end up with something that looks like this. Like that. Ooh, there we go. Oops, I'm missing a methyl group, aren't I? There we go. So now you've got something that's tertiary and it's allylic, right? The first one that we had was just a primary radical. It's not very stable. Whereas this one is tertiary and it's allylic. Okay, and you could draw the resonance contributor like this. Okay, I'm not going to draw it, but now you can see that the red proton is going to be the carbon hydrogen bond to the red proton, is how I should have phrased it, is the weakest carbon hydrogen bond. Give me a thumbs up if that makes sense now that you see it. Like, okay, well, now that I see it, it makes more sense. Right? Sometimes you just have to see these things a couple of times before you're like, yeah. Okay? Well, with that in mind, let's try similar type of exercise for the next one. Let me see. I'm just going to delete this. There we go. So for the first one, the answer was the red one. Let's try B. Let me put a proton here in blue. I'll put this proton in green and put this proton in black. Could anybody tell me which one of these would be the weakest carbon-hydrogen bond? Would it be the one to the black, the green, or the blue? Yep, I agree. I agree with all of my students. Yes, is that it's the green one. This one's, I don't think, a simple question, right? Because if you pull off the blue one, right? If you pull off the blue one, you end up with something that's doubly resonance stabilized. Hell yeah. Pardon my language, but this is resonance stabilized, my friends. Okay, you can draw it's allylic here and it's allylic here, but that is secondary allylic, right? This is secondary allylic. Whereas if I move this out of the way and I pull off the one in green, then I end up with, I didn't mean to do that. How did I do that? Son of a gun. Anyhow, what if I try this? Yeah, okay, cool. There we go. So if I pull off the one in green, if I break this bond homolytically, then I end up with this, which is allylic, but as you guys realized, it's tertiary allylic. And tertiary allylic is going to be more stable than secondary allylic, and so that's the answer. Yeah, so it's the one in green. Let's see, delete this. Delete. The next one, I find that all textbooks, not just Klein, usually try to increase the order of complexity, as you go along. But I think that C is actually simpler than B, and it's not simple, but it's simpler. And the reason why is because if you look at the double bond, I mean, this is an allylic position. It's got no hydrogens on it, and this is the only allylic position with a hydrogen. So that means it must be this carbon-hydrogen bond here. Right, that's the only possibility would be to break this one homolytically, like this. Then you end up with something that looks like it's primary, but it's not just primary, is it? It's, son of a gun, I can draw neither. It's primary allylic. Primary allylic. So it still has resonance contributors. And then I'll ask you one more. if I put this proton here in blue and I put this proton in red, these are both allylic positions. Could anybody tell me which one of these carbon-hydrogen bonds would be weaker? Would it be the one to the blue proton or the one to the red proton in D? Yep, everybody's right. It's the one to the blue one because you end up with something that's tertiary allylic versus primary allylic, right? So it's the one in blue, and that's because you end up with this. Okay, like this. This is tertiary allylic versus, oops, there we go, versus this, which is allylic, but it's primary allylic. There we go. All right, good enough. That's pretty good. All right, so you can see that section 10.1, you spend quite a bit of time talking about radical stability and making sure that you understand about the stability of radicals, and you know the difference between a resonance stabilized radical and one that isn't stabilized. So let's move on to section 10.2, where we're going to talk about common patterns in radical mechanisms. You remember when we looked at ionic mechanisms, we saw the same four patterns were covered over and over, like a rearrangement, a loss of a leaving group, nucleophilic attack, proton transfer. Well, here we follow patterns, but they're very different. So somebody's asking a question about this problem here. It says you're looking for the weakest carbon-hydrogen bond. So yeah, that's what we're looking for here. So all these bonds that I've highlighted, these are the weakest bonds, right? Because the weakest bonds are the ones that produce the most stable radicals, right? Weakest bonds produce most stable radicals. Does that help? So if we go back here and we look at bond dissociation energies, so we're talking about bond strength. Bond strength is inversely proportional to carbon radical stability, right? So what does that mean? It means if it's inversely proportional, it means the most stable radical is the one that comes from the weakest bond. Weakest bond. Okay? Because we saw that as you have R groups that surround a radical, it renders it more and more stable. Okay? So if we have, let's say, a carbon-hydrogen bond that produces a tertiary radical, it is actually weaker, right? It takes less energy to break that than if I had, let's say, a primary carbon-hydrogen bond, okay? Then that's going to take more energy to break. Why? Because you end up with something that's less stable. So when we were looking at this problem, which one was it? This one here. If we're looking for the weakest carbon-hydrogen bonds, okay, which in this case is this carbon-hydrogen bond, which in the second one is this one, in the third one it's this one, and in the last one it's this one. What do these bonds all have in common? These are the bonds that when you break them, you produce the most stable radical. So the most stable radical is going to result from the weakest carbon-hydrogen bond. All right, so let's get back into this patterns of radical mechanisms. So like I told you, we spent a lot of time talking about ionic mechanisms. So we talked about nucleophilic attack, proton transfer, loss of leaving group, carbocation rearrangement, okay? Well, we're going to see patterns in this section too on radical mechanisms. However, they're pretty different, okay? For example, radicals don't undergo any kind of rearrangement, okay? If we have this tertiary carbocation, heck yeah, that's going to undergo a rearrangement, won't it? This is going to undergo a methide shift to give you this, which is a tertiary carbocation, right? Here we have second, here we have secondary, here we have tertiary, but this is not going to undergo any kind of rearrangement whatsoever. But there are 6 key arrow pushing patterns that we're going to see repeated over and over in chapter 10. So let's take a look at those patterns right now. The first one is a homolytic cleavage. Good news is that we've already seen that when we talked about bond dissociation energies. We drew, or we saw at least the 2 fishhook arrows that result in a homolytic cleavage. So that's where we just take something that is not a radical, so not a radical, and we end up with something that is a radical. So now we have radical. So we go from no radical to radicals, okay? So how do we do that? Well, we initiate that either by light or heat. And the amount of heat that's required is going to depend on the bond strength, right? The weaker the bond, the less heat that's required. The light, well, the energy is going to depend on the wavelength, the frequency of the light, of course. And so sometimes you have to use ultraviolet light to break some bonds. The next is the addition to a pi bond. So if you start with a radical and you end up with a radical, right? Well, you take that radical, you add it to a pi bond, you do a homolytic bond cleavage kind of the pi bond, but you end up forming a new radical in the end. So you're starting it with 2 molecules, one that's a radical, one that isn't, and you're ending up with a molecule that is a radical. The next one is a hydrogen abstraction. You can guess that that's removing a hydrogen atom. Notice it's not proton abstraction, right? Because proton is H+, right? A proton is nothing more than a hydrogen nucleus. It's literally just a proton. There's no electron. Whereas in hydrogen abstraction, we're removing the entire hydrogen atom. We're taking the proton and its electron, okay? So if you have a radical, it removes or abstracts a proton, and then you're left over with a radical. The next one is halogen abstraction. So this is where a radical reacts with chlorine, bromine, fluorine, and iodine. We're not going to see those nearly as much, and I'll explain why. But this is where you start out with a radical. It reacts with chlorine or bromine usually, and we end up with a radical. And we're going to see that a few times. The next one is an elimination, which is really just the reverse of the radical addition or the addition to a pi bond. So this is where the radical on an alpha carbon is pushed towards a beta carbon to eliminate a radical atom or group. So let me get into some terminology here. The carbon that has the radical on it, okay, that's the alpha carbon, okay? So again, this is the alpha carbon here. So anything next to an alpha carbon is going to be a beta carbon. So that means that this is a beta carbon. So follow again. It says the radical on that alpha carbon is pushed towards the beta carbon to eliminate a radical. Okay, so we end up making a new pi bond here and we eliminate a radical. Again, it's just the reverse of the addition to a pi bond that you see here. So you just do this in reverse. Okay, anyhow, and we'll talk about that relationship in a few minutes. And then the last one is a coupling, which is where you start it with radicals. Okay, so radicals, and you end up with no radicals. So no radical or radicals. And this is just where 2 radicals come together and they make a new bond. Okay, and that's the reverse of the homolytic cleavage. So again, you probably noticed a couple of patterns here. Okay, the relationships among these 6 patterns is that you see the first and the 6th reaction that we looked at, the homolytic cleavage, that was the first one, and this was the 6th one that we looked at. Those are the reverse of each other, as well as the addition to the pi bond, which was the second one we looked at, and the elimination. Those are the reverse of each other. Now the hydrogen abstraction and the halogen abstraction, they don't work that way. Okay, they are not the reverse of each other. If you abstract the hydrogen, look, okay, if you abstract the hydrogen, well, the reverse is just the hydrogen abstraction as well. And the same thing applies for halogen abstraction. The forward and the reverse reaction both do the same thing. All right, so this whole relationship of the first and the 6th and the 2nd and the 5th being the, just the reverse of each other, well, it doesn't apply to the 3rd and the 4th, okay? So you can't apply it for all of them. All right, well, the steps in a radical mechanism are classified as either one of these 3 things: initiation, propagation, and termination. And this is what I told you, I think, before I even started recording the video. I said, something you've got to remember in radical mechanisms is initiation, propagation, and termination. They're kind of listed in a funky order here. It should be I would reverse these two because termination is the end, right? Initiation is the start of the reaction, okay? Termination is the end of the reaction, and propagation is what propagates the reaction. It's what keeps it going. So how do we initiate a radical mechanism or a radical reaction? Okay, not a radical reaction. The way that we do that is we have to initiate it by doing a homolytic bond cleavage, right? We have to start with no radicals, but we're going to start by making a radical right away, right? And again, the only way that we've seen how to do that is to start with something that's not a radical and turn it into a couple of radicals by doing that homolytic bond cleavage. And again, I told you that the homolytic bond cleavage can be promoted either by heat, okay, or by light, depending on the situation, okay? So that's going to depend on the reaction conditions, so we'll talk about that more. But propagation is what happens when a radical reacts with a non-radical and you end up with a new radical. So you start with a radical and you end with a radical in propagation. If we just back up, let's repeat this. In initiation, you start with no radical and you end up with a radical. Okay, so that's initiation. Propagation, you start with a radical, you end with a radical. So what are the types of propagation that we can have? Well, there's 4 types. You can have the addition to a pi bond, which we saw already, right? That was the first mechanism that we looked at. You can have the elimination. That was the 6th one. Anyhow, I don't remember their orders, but these two are the reverse of each other. And then we looked at the hydrogen abstraction and the halogen abstraction, okay? And what, again, these 4 patterns have in common, and every single one of them, you start with a radical and you end with a radical. Now, if you're like, well, I've just looked at this for 20 seconds and I don't have it all, I don't have it all down pat yet. That's normal, okay? You're going to have to take a look at some mechanisms, and we're going to take a look at a mechanism or two this morning, but you want to make sure that you study these, that you're aware of what an addition to a pi bond is, hydrogen abstraction, halogen abstraction, and elimination, and that you also know that these fall under the greater umbrella of propagation reactions. Well, we got to cover the termination, don't we, right? Because I said there was initiation, that was the homolytic bond cleavage, there's propagation, and then there's termination of my slides, right? Termination occurs when 2 radicals come together to form a non-radical, okay? Termination is probably, the fastest one to learn, because any 2 radicals can come together, and if they form a new sigma bond, you're done. Okay, you're toast. You've eliminated all the radicals, so the radical mechanism is over, right? It's the end of the road. So you have to be aware of initiation, propagation, and termination. And you can see here in my slides, it says the complete definitions of these are going to be discussed even more as we progress through the chapter. I'll give you more information on these. Well, with that in mind, let's see if we can draw some fishhook arrows for each of the following processes. We're starting it with a tertiary radical in A. It's reacting with some hydrogen bromide, some HBr, and you end up with a radical. So this is a hydrogen abstraction, isn't it? Right, because we have the hydrogen in the HBr. I'm going to redraw the molecule because you need a Lewis structure in order to get these to work, okay? So this is a hydrogen abstraction. Again, how do I know that? Because I'm taking the radical and I'm removing this hydrogen, right? And I'm putting it over here. All right, well, let's draw the curved arrows for that. So let me show you the nuances here. Since you're forming a new bond, right? This bond that I have circled in black, that's the new bond you're forming. The electrons kind of have to meet in the air, right? You have one fishhook here, and then from this sigma bond, the hydrogen is going to take one of those electrons and you're going to make the new sigma bond. So when you have the 2 fishhook arrows meeting in the air like that, that's showing the formation of a new bond. And then the bromine is ending up with an unpaired electron, and that's a little faster to draw. It just comes off like that. So there's your hydrogen abstraction. So again, the arrows connect in midair to make a new bond. We could even make a note of that. So arrows connect in mid-air to make a new bond. Now, just like, curved arrows that we saw in ionic mechanisms, it doesn't matter where they meet. If you're like, well, my curved arrows met, over here because that's where the bond's being formed, that's fine. There's nothing wrong with that at all. That's perfectly fine, okay? There you go. All right, well, the next one, we're starting out with a double bond and a bromine radical. and the bromine is being added to that. So this is an addition to a pi bond, isn't it? So let's scribble that in here. B is an addition to a pi bond. Okay, so what are we doing here? We're forming a new bond over here. So we're going to take one of the electrons from the double bond, and we're going to take the unpaired electron here. There's our new bond being formed. And then we're going to make this tertiary radical. So one of those electrons is going to go over here like that. And there you have it. There are two mechanisms, or two fishhook arrow mechanisms. And even though fishhook arrow mechanisms are quite different than ionic mechanisms, all of our proton transfers, carbocation rearrangements, etc., I think that if you understood that, it will definitely help you with this. You know, anything that you learn in organic chemistry will be beneficial to learning something else in the class, won't it? All right, there we go. So that covers section 10.2. Those are the those are the types of radical mechanisms that we're going to see. And again, they're going to come up over and over. And yeah,